All right, it's 11:50, so we're gonna get started. Today we are gonna go over some functions and relations. This is gonna be coming up in your quiz soon, so just wanna make sure that feeling good about problems with functions and relations. All right, so for this first problem, we're doing a one-set arrow diagram for the following relation. And we've got the domain and the codomain are both that set A. And the rule is that two elements are in the relation if their sum has a remainder of 0 or 4 after division by 7. All right, so I'll let you go ahead and work on this one for a couple of minutes, and then we'll come back together and talk about it. And just to clarify real quick while you're working on it, so the rule, it might be easier to think of it as x plus y mod by 7 equals 0 or 4. And there are only a few numbers that will satisfy that with like how many sums we can have here. So it might be helpful to make a list of the possible answers, like the possible sums that would fit this rule. All right, it's been a couple minutes, so let's get going on this one. So for a one-set arrow diagram, we're always going to want to have just kind of like a circle for each of these points. So this is going to be 0, 1, 2, 3, 4, 5, and I need one more. Oops. All right, so what are the possible sums that will satisfy this rule?
3, 4, and 6, 1.
Let's see, 3, 4, 6, 1. Yeah. So that's the sum. 3 plus 4 is going to be 7. So that'll have a remainder of 0 after dividing by 7. And you said 6 and 1. So that'll be the same. It'll be to 7. Okay, what else can we add to both of these arrows?
0, zeros, I guess.
0, 0.
Yes.
Okay, and that sum will be 0. So it'll have a remainder of 0 after division by 7 as well. So with these two arrows right here, so we can actually add arrows going the other way as well, because 3 plus 4 equals 7, and 4 plus 3 also equals 7. All right, what else?
5 and 2.
5 and 2. All right, and that one can go both ways as well. Okay, so that is most of the ones, let's see. Yeah, I believe that's all the ones that will add up to 7, but remember we've also got an option of remainder of 4. So what other relations can we do?
5 and 6.
5 and 6, yeah, exactly. Because their sum is going to be 11, so the remainder will be 4.
Seven and 4.
7
Or
and
there is no 7. Sorry.
0, 4.
0, 4, yeah. And that one can go the other way as well.
1, 3, and 2, 2.
Exactly. All right. Are we missing any?
Is number 4 to go to itself?
4.
Because oh no, sorry. Yes.
Yeah, 4 plus 4 would be 8. So yeah.
Okay. Sorry.
No need to be sorry. Okay. So there's our one set arrow diagram for that. Are there any questions on that problem? Okay. We're going to move on to problem 2. And for this one, we want to decide if the relation is reflexive, antisymmetric, or transitive. And if it fails the property, give a specific counterexample. So you don't need to use any proofs on this problem, just decide whether it fits these properties and if it doesn't have a counterexample. So I'm going to give everyone just a couple minutes to make sure that they get this problem down, because we're going to split off into breakout rooms and everyone's going to work in groups to solve this one. So I'll just give you, most important thing to get down is we've got this, the set and the relation, and make sure that we're doing all 3 of these properties. Okay, I'm gonna go ahead and send you off now, and I'll have you work for, let's say, about 7 or 8 minutes. And let's see. See, did it not have you go off to a breakout room, Brady? Oh, I think you're muted.
Did you assign them just like automatically? Because I think I joined one of the breakout room.
Yeah, it looks like there's still a couple people in here that have not joined. I'm not sure if it just, see, Brady and Sonora, did it give you an invitation to join a room?
Did you give them like 7 or 8 minutes?
Yeah, I set a timer for 7, but I'm gonna give a little bit longer than that, especially since that first breakout room is struggling. Yeah, I'm not sure.
I feel like giving them 5 minutes is enough. I'm not sure if they still like talking to each other or.
Okay, I'll do a. Let's see. Yeah, I'll just close them. All right, looks like everybody's back. So let's just go over the answers for this one real quick. Since all of you worked on it, we won't spend too much time. Is this relation reflexive? You can answer in the chat or raise your hand.
I don't think it is.
Okay, did you find a counterexample?
Not specifically, but I think maybe.
Okay, just go ahead and give me what you got.
Well, wouldn't like 1 and 3 not be reflexive with itself?
I think that would be more related to symmetry. So remember, reflexive is if a relation is reflexive, it means that every element is related to itself.
Right.
So, for example, is the element?
I mean like 1 and 3 as a set.
Oh, okay, yeah.
Because
Yeah.
this is the power set, right?
Yes, sorry. So
And that's not related to itself, right?
yeah, exactly. So the set 1 and 3 related to the set 1 and 3 is not in the relation.
Right.
That's exactly right. Because the intersection of these two sets would not be the empty set.
Right.
Okay, nice job. Antisymmetric.
I would say yes.
Okay. Let's see. How come?
Because like say 2 and 3, they don't have an intersection going either direction, so that their intersection is the empty set. So
Intersection.
going either direction.
So the set 2 related to the set 3?
Yeah.
Okay, so let's look at this. So the set 2, whoops. So if that is, let's see, in the relation, so is 3 related to 2 in the relation as well? Whoops.
Yeah.
Yeah, so since this one is antisymmetric, that shows that this shows that it is symmetric, because you can switch the elements and it's still in the relationship.
Okay.
So antisymmetric, if there's any elements that are symmetric, it can't be antisymmetric.
That makes sense. Sorry.
I have a question about this one.
Mhm.
For the anti-symmetric, so the A need to be like not equal to B, or like it can be the same. Like let's say 2 equal to R, just say that. So can like 2 element be the same?
Do you mean, so like, sorry, can you give me an example of what you mean?
So like the set AB is belong to the power set S times power S set S, right? So if like 2 elements from A and B are the same, can it be like that, or it need to be different?
Do you mean
Like 2 equal belong to R, just like say it.
to like the set 2
2.
like that?
Yeah. So A is 2 and B is 2. So like, can it be like that for the symmetric? I mean for the anti-symmetric.
For anti-symmetric, well, so So this is actually not in the relation because the intersection of these
Yeah,
two
I understand, but like just let's say like it is in the relation. So like for
Oh,
the for the
okay, yeah.
antisymmetric, yeah.
So remember that for to prove that any when you're looking at symmetry, you're saying it's an implication. So you're saying if A and B is in the relation, then BA is also in the relation. Yes,
Yes, but like A and B can be the same, right?
they can.
Uh-huh.
But yeah, that would be possible, just not in this problem, because in this case,
Yeah,
we
yeah,
have
I
false
got it.
hypothesis.
Got it.
Okay, awesome.
So yeah, it is possible to have a relation that's symmetric and antisymmetric if the only symmetry is like an element pointing to itself, like that case.
Element.
Yes, I think so.
Okay.
If you have 1, 1, and 2, 2, and 3, 3 in a set, it's both symmetric and antisymmetric.
Yeah, I'm pretty sure there was a question on a quiz at one point that tested on that.
Yeah, I think the problem set. All right, last one, transitive. Does anyone have an answer for that?
I think it is transitive.
Okay. Do you have an example or an explanation?
I think that is it because we can have, for example, 1, 2, and then we can also have 1, 3, and we also have 1. We have 2, 3. Is it like? I'm not sure if I.
So, okay, yeah. So that would be, let's see. Let me make sure that I'm getting it right. So it'd be 1, 2, 2, and then 2 to 3 and 1 to 3.
Yes. Yeah.
Okay. Yeah, so that's true. But remember that for transitivity, that has to be true for every single element. Every single relation has to be transitive in order for that to be true. So that case is transitive, but there actually are examples of elements that would not be transitive. So did anyone find an example of a relation that would not be transitive? So let's just take one related to 2 and 2 related. This is a lot of curly braces and parentheses all mixed together. Okay, so do we agree that these elements, oh, whoops, I didn't mean to put 3. I meant to put 1. Do we agree that these elements are both in the relation?
Yeah.
Okay, but for transitivity to work, then we would need to have 1 be in the relation as well. And is that true?
No.
Yeah. So since there is at least one example of that, then we say it's not transitive.
Then that means that throughout the whole set, like for example, when we meet reflexive, antisymmetric, or transitive, and all this, it has to be throughout the whole thing. So even if there's one exception when it shows the otherwise.
Yeah, exactly. That's gonna, yeah. So for every single one of these, it has to be every element, which is why if you're proving that something is transitive, it's important not to have like one example, because we need to have some kind of proof that is general for every element.
And that means that there's possibility that it could be neither like antisymmetric or symmetric, like it can be neither, because we have cases of, okay, thank you so much.
I'm still confused why 1, 3, 1, 3 is not in the relation. Is it because of the A intersect B?
Yeah.
Can you explain that?
Yeah, so this is saying that A and B are in the relation only if their intersection is equal to the empty set. So if we took the intersection of 1, 3 with 1, 3, what is their intersection going to be?
Would it be 1, 3?
Mm-hmm.
Okay, I see.
Which isn't going to be the empty set.
Thank you.
Mm-hmm. All right, any other questions on that one? Okay, so now we're going to, this is going to be a transitive proof. So prove that if R is a transitive relation on A, then R inverse is a transitive relation on A as well. All right, so I'll give you a couple minutes to look at this problem and see if you can figure out like about what the outline would be, and then we'll go through it explicitly together. All right, let's work through this one. So remember, if we're doing transitive relation or a transitive proof, we've got to keep it general. So let's just let some A, B, and C in the set A. All right, so what would be relations that would create a transitive relation for R?
A to B and B to C.
A to B and B to C are in R. And since R is transitive, then we also have A and C is in R. All right, so then the inverse of R has what elements?
C to B and B to A.
C to B and B to A. All right. And what else does it have if A and C is in R?
C to A.
And CA are all in the inverse. All right, so then we have that these three sets together make the inverse of R transitive. So since CB, BA in the inverse implies that CA is in the inverse, then the inverse of R is transitive. Okay. Any questions on that? Okay. So let's go ahead and move on to the problem on functions. So we're going to decide whether this is one-to-one or onto. And then if it is not, then we have to give a counterexample. So before we try and do any proofs or try and figure this out, let's just look at this problem and try and figure out if it is one-to-one and if it is onto. So I'll give you just a quick minute to try and figure these out, and then we'll work through proofs or counterexamples. Okay. So let's go through one-to-one first. Okay, is F one-to-one?
I want to say yes.
All right, did anybody get anything different?
I would say no.
Okay, so what are either of your justifications? Did you find a counterexample or do a proof?
I don't have a specific counterexample, but it's a quadratic function, so it'll be a parabola, which means most x values, or a lot of y values will be, what am I trying to say? It won't pass the horizontal line test.
Yeah, exactly. All right, so did anybody else find a counterexample?
Like 2 and -2.
2 and -2. Let's see. Let's see if that would work. I'm not.
That one actually doesn't work. Never mind.
Okay. All right. Anybody else find a counterexample? Okay, so let's take -1 would end up being 1 minus 4 plus 1, which gives -2. And f of -3 would end up being 9 minus 12 plus 1, which is also -2. So we have that f of -1 equals f of -3 because these two answers are the same, but -1 is not equal to -3. So f is not one-to-one.
So in general, to find out if a function is one-to-one, could you set it to itself and then see if there's any solutions, and then just assume from that that it's one-to-one or not?
Yeah, so like in this case, we could take, if we let f of x equal f of y, we could let x squared plus 4x plus 1 equal y squared plus 4y plus 1. We can cancel out these ones, and we end up with x factored out of x plus 4 equals y factored out of y plus 4. And this factorization leads to, we have 4 cases. So either x equals y, x plus 4 equals y plus 4, x equals y plus 4, and x plus 4 equals y. And these two are where we're going to run into problems because this shows that x and y are not equal. Does that make sense? Awesome.
Also, it needs to be like all four these four case, or you just need like one of these four case.
Yeah, we would need, in order for it to be 1-to-1, we would need to show that in all 4 cases, we can prove that x equals y somehow.
But like, why did you get the x equal to y plus 4?
So that's just because of this factorization. When we've got 2 like factors on either side of an equal sign, then we need, like, in order for them to be equivalent, they need to be able to equal each other. Does that make sense?
Yeah.
Okay. All right, so let's go on to. Did anybody find an answer for this one? I know onto is sometimes a little bit less instinctual, but.
It's not onto.
Yeah, did you find a counterexample?
Yeah. Not a specific one.
Okay.
I mean, when any, probably a low negative number, it would never map to.
Mm-hmm. Yeah, did anybody work through a counterexample? Okay, so let's take -4 is equal to x squared plus 4x plus 1, and we want to somehow show that x is in the set of real numbers. So how would we solve for x here?
So we have like x squared plus 4x plus 5 equal to 0.
Okay.
And then we have like x squared plus like 2 times 2x plus 4 plus 1. So it's gonna be always greater than 1, not gonna be equal to 0.
So x squared plus 2x plus 2 plus 1.
No, I mean like 2 x squared plus 2 times 2x plus 4 and plus 1.
Sorry. Okay, so 2x squared.
No, x squared plus 2 times 2x
Times 2x.
plus 4 plus 1.
Okay.
So we have like x plus 2 square plus 1
X plus 2
square
squared plus 1.
x square plus 1. So it's going to be always greater than 1.
Okay, yeah. And we can also use the quadratic formula here as well to find that x could not be a real number. So for that, we would do, let's see. So starting from the same point, I'll just do method 1 and method 2. So if we set x equal to -4 plus or minus the square root of 4 squared minus 4 times 1 times 5 over 2 times 1. And that comes out to -4 plus or minus the square root of -4 over 2. And this -4 means that we don't have a real number. So x is not in the set of real numbers, which means that f is not onto. All right, let's go on to, well, first, are there any questions?
Like, is this an negative number, or it must be -4, or we can take like whatever we want?
Yeah, so yeah, this -4, I think you're asking, could you use a different number there? Is that what you mean?
Yeah.
Yeah.
Like different negative number.
Yeah, exactly. As long as you just have some, this is just one counterexample, but there are lots that you could use. All right. Okay, so now we have a function and we're told to prove that f is 1-to-1 and onto, so we're kind of given that it is and we just want to prove it, and then find the inverse function of f. So I'm just going to work through this one right now so that we still have time to do the counting problem at the end. So let's get started on this one. So how do we start a 1-to-1 proof?
So do we have to find like pick like two different elements and then we have to prove that the f's of those be different? Like we have, yes, S1.
So we could let x and y be in the set 1 to infinity, and then let f of x equal f of y and show that x equals y. So that's the basic recipe for any 1-to-1 proof. If f of x equals f of y, then we have x over x minus 1 equals y over y minus 1. And we can multiply across to get x times y minus 1 equals y times x minus 1. And we'll multiply this out, have xy minus x equals xy minus y. Then these two terms cancel out, and we have negative x equals negative y, so x does equal y. Therefore, f is 1-to-1. All right, does that make sense to everyone?
Yes.
Hey, awesome. So now let's do an onto proof for this one. And this is one that onto proofs are tricky. We definitely noticed that in the homework. So for f to be onto, we want to start by letting some element, let's say y, is in the set of 1 to infinity. Or actually, I believe the slides use b, so we're going to use that just for clarity's sake. So b is going to be in this set, and we want to show that there exists some element a that is in here. I'll just, okay, I'm going to make a quick note right here. This is the codomain, and this is the domain. That's something that is important to keep clear in these proofs because the codomain and the domain are not always the same. So we let some element be in the domain such that f of a equals b. So in this case, we would have b equals a over a minus 1. All right, so there are a couple different ways to prove it. Does anybody want to go from here, say where they would go?
Get the inverse of b.
Get the, sorry, what do you mean by that?
Well, like when we were first learning onto, we would like get the inverse of b and then like plug it in to the original equation.
Okay, yeah. Yeah, that works. For this one, there might be a simpler method. Basically, we want to show, what we're really trying to show here is that a is in the set from 1 to infinity. So we can actually take, let's see. I'm trying to think of the best way to explain this. All right, so let's say, well, in order for this, we know that this outcome has to be we know that we're basically given that this is a real number. So we don't want to assume that, like, sorry, this is given. So we really want to show that this is a real number. So in order for it to be a real number, then we would have to have a minus 1 is greater than 0. Yes, otherwise we would have issues. So that also means that a is greater than 1. So if we plug, I guess plug is maybe the wrong way to explain it, but we can kind of put these back into the equation and say that f of a is greater than 2 over 1. Does that make sense? Or not f of a? My goodness. So b, we're already given that it is from 1 to infinity. Yes? So if this term is equal to b, then we know that it is at least 1. So in order for it to be at least 1, then we have to have that a minus 1 is greater than 0, and we have to have that a is greater than 1, which is just a derivative of, we just added 1 to both sides here. All right, so now we have that b equals, like, b is going to be, the top part is at least 1, and the bottom part is at least, or, oh my goodness, sorry everyone. Okay, the numerator is going to be greater than 1, the denominator is going to be greater than 0. So that means that the whole thing is at least 2 over 1, greater than or equal to 2 over 1. Does that make sense? Okay, so if this, oh my goodness. So this tells us that a is going to be at least 1. This is really the important part right here, because if a is at least 1, then that means a is in the set from 1 to infinity. All right, does that follow? I know I got kind of lost in there.
Can you talk about it again, like one more time?
Yeah, okay. So we are given that b is in the set from 1 to infinity. And we want to somehow show that a is in the set from 1 to infinity. So since this term has to be greater than 1, then we're given that a minus 1. So let's see, I'm just going to erase this bottom part because I think that that's not as relevant. In order for this whole term, the a over a minus 1 to be greater than or equal to 1, then the denominator has to be greater than 0. Otherwise, it wouldn't be, b wouldn't be in this set, which we are given. So this implies that a minus 1 is greater than 0. And then if you add 1 to both sides, we get that a is greater than 1, which is what we needed. We needed to show that a is in the set from 1 to infinity. Does that make more sense?
Yes.
Okay.
So that's what is showing there from 1 to infinity, that's B domain, right? Or like B, like from 1 to infinity, that's its domain, or that's its codomain?
So B, this part right here.
No, down where you like are pointing to B. Yeah.
Right here, yeah. So that is just saying, let's see, we know that B, we started by saying we're gonna let B be in this set. Like we're just assuming that B is in the set from 1 to infinity. So so this arrow is just to kind of restate that, that B is I guess that would be a better way to show it, is b is in 1 to infinity, which means that a over a minus 1 is also in the set from 1 to infinity.
Okay, that makes sense.
Okay. All right. Sorry, I kind of messed up with the time there for a little bit. Do we still?
Sorry, I had one confusion. How do we know that? Wouldn't it be possible to have a be a negative number and still have that fraction turn out so that b is positive?
If a was a negative number, then the entire term would end up being negative, and then it would not be in the set from 1 to infinity.
So the term a over a minus 1 would turn out less than 1 if a were negative, right?
Exactly.
Isn't that it? Okay. Okay.
But
Also,
I can.
never
But
found the inverse function.
Hmm?
We never found the inverse function.
Oh, yes. Inverse function. That one's not super, for the inverse function, you can, you just switch the variables, if that makes sense. So we would have, I'm just going to draw a little section, y equals x over x minus 1. Then we would just switch the x and y's. So x equals y over y minus 1, and then replace this with f of y. So this would be the inverse.
so it's like the same.
Yeah, basically.
Don't you have to
That won't always
solve
be the case.
for y?
F, let's see. Let's see. Nancy, do you know, because that's what the solution slides had. Would we need to solve for y?
Yeah, I think he
Oh,
would
because
solve
if
for
it's
y
negative,
and
and then it's going to be less than.
Oh gosh. Okay. We're a little bit out of time, so everyone who needs to go ahead and go, but anyone who wants to walk through this, feel free to stay. And then also for people who are leaving, see if you can work through this problem on probability on your own, and if not, come to office hours or ask on Piazza.
yeah, I think he would just let y equals x over x minus 1. And you would just find out, yeah, I think he would, yeah, it's just going to be y over y minus 1. It's the same.
Okay. That's what I was thinking.
I think like it's x need to be equal to y over x minus 1. It's not y minus 1.
Well, isn't it in terms of f of y right now, not f of x? You could solve for y, so it would be in terms of f of x, right?
Yeah. So I guess, sorry, it would be more appropriate for this to be that notation.
I'm still confused about it. So we have like y equal to x over x minus 1. And then we like switch to, so we got like y times x minus 1 will equal to x. And then, yeah. Which is like not like this. I'm still confused. Like, can you?
I think the inverse of for one, the Zoe rule, like the f inverse y, that one should be equals to x over x minus 1. Because you have the inverse and you input y, which will give you the, let me see.
Can we say just basically like we can solve x for y? So you have the second function, right? The first one you set y equal to x, and the second step you set x equal to like So x by y. So you can have that, right? That's what it means to find the inverse function.
Oh my goodness. Sorry, I'm just looking at the chat as well. I'm trying to see.
No, I think you're right. Yeah, you saw it right.
If we had x equals y x minus 1, and then switch the variables, we would have y equals x, y minus 1.
Oh, so do you need to
Oh, yeah.
switch the variable?
So yeah, let's go ahead and here. I'm gonna add in a new page here real quick and we'll do it. Okay, so in the chat we had that, so y equals x over x minus 1.
Yeah, that is the like the original function.
Sorry, what?
Never mind, never mind.
Okay, so that would change, that would be y x minus 1 equals x, yes? Okay, and then so you would switch the variables here to find the inverse and you would get
Oh, I see. So
y
just like
minus 1 equals y, and it would still end up with the same y over y minus 1.
I got you.
So I'm not sure if this inverse is supposed to be there or not. That's what's in the solution, but I'm not positive. I think it would just be f of y, which f of y is the inverse of x. So
Yep, I got
yeah, either way you would still get the x equals y over y minus 1.
Okay.
Sorry for all that confusion, everyone. That was, yeah, this problem was a little bit rough. So if you have any other questions about that, please feel free to ask them. But yeah, if that's all, then I can stop the live share, but I just want to make sure there's not any more questions.
I just have a quick question about the quiz for. So like in the practice quiz, it's like is as long as the actual quiz. So like the actual quiz will be like 80 minutes.
So the actual quiz will still be an hour, just like all our other quizzes. So.
But I mean like as long as it means like the problem will be like that long.
I can't tell you exactly how long it will be, but the goal is to have it that you could complete it within an hour. That's really the only.
Yeah, because I got it. Because like the last quiz is like it is a little bit too long to do in 1 hour. So
we had a lot of feedback saying similar things. So we're taking that into consideration when we're creating quiz 4. We want to make sure everyone can get it done in the hour.
Right. That's great. Thank you.
Mm-hmm.